Hi everyone, this is Hardik from fuzzing.in. Thank you for watching my videos. In today's video, we are going to see the recent OpenSSL vulnerability, that is CVE-2023-0286. In this video, we are going to see what is this vulnerability, and we will have a look at the code diff and how it was fixed. And then we will see how can we write a LibFuzzer harness to find this vulnerability. Let's see how can we fuzz that. So let's start. So first thing we will see is that we will go to the OpenSSL's official advisory, and when we go to this URL, we can see that this was released on 7th of February 2023. That is like a week back, and there are a couple of vulnerabilities which has been fixed in this release. So the first one we can see is x.400 address type confusion in X509 general name. So that is CVE-2023-0286. This is what we are going to see. And we can see that the severity for this vulnerability is high. And there is some details which has been given over here. That is, this is the type confusion vulnerability, and it is because there are x.400 address, the way they are processed inside an X509 general name. So we'll go ahead and we will see the code how it was fixed, and it also gives us a hint that what may be the possible root cause. So we can see that x.400 addresses were passed as ASN1 string, but the public structure definition for general name was for this particular x400 address was ASN1.type. So this is a type confusion vulnerability. So we can see that there are different versions which are vulnerable to this. And if you are using OpenSSL 3.0, then you should use OpenSSL 3.0.9. That is the latest version where this vulnerability was fixed. And if you are using OpenSSL 1.1.1, then you should upgrade to 1.1.1.t. And if you are using OpenSSL version 1.0.2, then you should upgrade it to 1.0.2 So, and this issue was, like, as you can see, it was reported on 11th January by David Benjamin, who works for Google, and the fix was developed by Hugo. So that is one vulnerability which we are going to see. And if we see, there are few other vulnerability which are like of moderate severity, so we are not going to see that. So I think total there are 7 vulnerability which has been fixed over here. So we will see how do we use OpenSSL test case first, and then how can we get this replicated, and then we will do the some root cause analysis. So before, I think if we start with replicating of this issue, let us go ahead and actually look at that particular release and see what has been fixed over there. So we'll go ahead and see this particular GitHub branch or GitHub tag, and then in that way we can see the commits. So if we simply click on the commits, we can see that there are like a lot of commits over here, and it is not possible for us to identify the issue. But luckily, if you see it over here, you can see that the CVE ID is mentioned over here, that is CVE 2023-0286. This is what we are going to see. So most likely this is the patch which fixes this. So let's go ahead and see what has been changed in this release. Okay, so you can see on the left hand side there are like couple of files which has been changed. So one of them is inside crypto directory, inside x509 directory, and the file name is v3_ge_c. So this is the source file, and then there is one include file, and then there is one test case which has been added for this. So if we see this particular file v3_ge_c, then we can see that there is a very simple change which has been made to fix this vulnerability, and that is when we see there is a switch case, there is which checks for a type, and if it is of type gen underscore x400, then previously the function which was called was asn1 underscore type underscore compare, and then you can see that there are two parameter which were passed to this function, that is a pointer d dot x400 access address, and b pointer d dot x400 address. So it has been replaced by asn1 underscore string underscore compare, and thus parameter are same. And also you will see that inside the header file, that is x509v3.h.in, you will see that the structure general underscore name underscore st, the type of x400 address has been changed from asn1 underscore type to asn1 underscore string. So these are the change which has been made to fix this particular vulnerability. And if you see, there is one regression test case which has been added inside v3 name test.c. So this regression test, it's simply using 2 bytes, that is 0 cross a3 and 0x00. So we will see when we replicate this issue, we'll see that how can we find the same thing using LibFuzzer. So this is a simple fix for this vulnerability, and nothing much complex. So now what we can do is that we can actually clone this repo on our system, and then we will go to this particular branch, and then we will actually compile the test case. We will run the test, and the test should get passed, and then we will move to one version order, that is 3.0.7. We will use the existing test case from 3.0.8, and we will see how can we replicate that issue. So let's go ahead, and first thing we need to do is we need to clone OpenSSL repo on our system, and then we need to compile it. So let's go ahead and see that. So the command to clone OpenSSL on our system is git clone, then the URL, that is https github.com openssl/openssl.git, and this is something you can simply go there on this URL, that is github.com openssl and click on code. Simply copy this URL and go to your command prompt and simply run git clone and type this. So in my case, I have already cloned this, and I have cloned it as a OpenSSL underscore vulnerable version. So actually, let me go ahead and see the patch version first, so that we can get the test case. Okay, so I have cloned it two times. One is for the vulnerable version and one is for the patch version. So what we are going to see right now is the patch version. And if we see that particular file, that is crypto slash x509v3gen.c, this should contain the fixed code over here. So if we simply go ahead and the general name compare, right, we need to go to that function. So you can see this is the vulnerable function which was fixed. And if we see over here, so if the a type is gen underscore x400, then in this case it is calling asn1 underscore string underscore compare. So this is the fixed version, and as you can recall, like we have seen the source code. So to fix this vulnerability, they have replaced the previous file, that is asn I think type compare to asn string compare over here. So this fixes the vulnerability. This is the only change, and there is no other change which has been done for this. So now what we can do is that we can simply configure our OpenSSL. Okay, let me use the build directory. So I will simply use this command, that is /configure -- prefix is equal to home, my username, and research OpenSSL underscore paste. This is directory, and I will create a build directory over here. So what it will do is that when I do make install, it will not install system wide. It will simply install all my OpenSSL library to the build directory. So that way I can avoid installing like this version on my entire system. I can simply use it for the testing purpose. So that's why I have used prefix over here. Okay, so you can see that this configuration command, when I use it, has generated the config file, and Now what we can do is that we can simply do make and make install. So I'm using make dash j4. That means that it will use 4 cores, and then we are simply using @ make install. So it will basically compile our OpenSSL version, and then it will install it inside that particular directory, that is OpenSSL patch and build directory. So let's go ahead and hit enter, and let's see how much time it takes. Okay, so you can see that it is installing our OpenSSL build now. So I think we are almost done, and now I think we can simply go ahead and see. We can try to run that particular test case which was added for that particular vulnerability, and let's see what happens. And now what we can do is that we can go to test directory, and here we can see that there is something called v3 test over here, v3, and we can simply run this file. So let's run v3 name test, and we can first we will use the help option to see what kind of tests are available. So we can see that the valid options are help list test value. So let us do one thing. We will use list command to see what are the tests which are available over here. So there are actually 2 tests. First one is call run underscore cert, that is like 1 to 10, and second one is test general name compare. So if you recall, this is where the vulnerability was present, and a new test case was added for this, as you can see it over here, right? So it is over here. So what we are going to do now is that we will run the second test, and we will see if it fails or if it passes. So we can simply use the same command. We can simply use v3 name test dash test, and we can give the test which you want to run. So we will give 2. So as you can see it over here, in my case it is causing a set fault even though my version is actually paged. So the issue because why this is happening is because it is not taking the library which we have compiled. It is taking the default system library. If you see the path over here, right? So it is using lib AR64 Linux, and it is over here. So it is not taking the path. Actual path should be inside the build folder. So if you go to our build directory over here, so if we go to the build directory, you will see that there is a lib directory over here. So this lib directory contains the compiled file. So our test was not taking this file, but it is taking the system file, as you can see it over here. Use load library path. So let's use that command, and then we will see if it is working or not. Okay, so the command which we need to use over here is that we need to use ld underscore library underscore path, and we need to give our build and lib directory over here so that it can use the latest compiled file. And when we give this path, and then when we run this v3 name v3 name test, then as you can see that if we use option 2 test 2 over here, so it is getting passed over here. Remember previously when it was taking the system file, we're getting a sec fault. It means that the version which is installed on our system is vulnerable. But when we compiled the patch version, and when we use that compiled file, in that case you can see that the test is getting passed over here. It means that the vulnerability has been fixed in the patch version. We are not able to replicate that. Now what we can do is that we can take this particular test case from our patch OpenSSL version, and we can copy this test case to the vulnerable version. So for vulnerable version, what I have done is that I have cloned my Git repo, and I went to version 3.0.7. If you are not sure how do you go to a particular version, then I will recommend you to go to my channel and look for my previous SSL video where I discussed another SSL vulnerability, and there I have shown you how to change version using Git. If you are familiar with Git, then it should be very simple and very straightforward. You can simply clone the Git repo using this command, that is OpenSSL, and then you can simply do git checkout and that particular version. So I will suggest you to refer to my previous video so that you can save some time over here. So let's go to the vulnerable version now, and we will see the same file which contains the vulnerability, that is crypto/x509/v3gen.c, and we will go to that particular function, that is general name compare, which is over here. And here if you see, right, the a.type, so there is a switch case, and if it is John underscore x400, then the function which is called over here, that is asan1 underscore type underscore compare. So this function contains the vulnerability. So if we see the fix, right, you can see it has been, this function has been removed, and it has been actually replaced by this function, that is asan1 underscore string underscore compare. So this is our vulnerable version, as you can see, right, because this contains the vulnerable call over here. Now what we can do is that we can simply copy that particular test, so we can modify the test file actually, and let's see. Okay, so I have opened that, and we want to go to gen name, right? So we will first verify if this new test case which has been added over here, so it is like added on line 647. So if this is there or not, so you can simply go there. Okay, yeah, so I have manually added this test case from the patch version over here. So basically I have copied pasted this line from here uh, to here. So as you can see, I have simply added one regression test case, that, and it contains simply like two bytes, that is 0 x83 and 0x00, right? So this 2 bytes has been added over here, and if you see where it was added, so this is actually an, I think it's an like array kind of thing, right? So let's go ahead and see which variable is that. So yeah, over here, so it is like a structure that is gen name data. Inside that we have one array that is like der, and there is a length, and this is the variable. So basically this is the der and this is the length of this data. So if you count the length, like the number of variable like this, it will be 21 over here. Over here it is 21, and similarly if you see over here, right, let's say over here, so there are 3 characters, so the length is 3. So in our case, if we go to the end, so these are the value, and the length will be 2 over here. And now if you see like what this test case actually does, so you need to understand this code, and you can see that there are two general underscore name variable which has been taken over here. This is the structure which has been again fixed over here, as you can see in the fix file. Like if you see over here, right, so this is the structure, and the type has been changed from asn1 type to asn1 string, right? So this is the structure, and there is a malloc call which basically like allocates some memory for all this variable, like all this variable, it saves them. And so there are two variable name sa and name is b, and there are some sanity checks over here, and then there is one for loop, and what it will do is that it will basically take each of this array element, like this one, this one, this one, and then it will generate two names, and it will save it in the array. So this is the like function d2i general underscore name function, and it will basically take this uh, character, it will take the length, and then it will generate some name. So we are generating two names over here, and then it is comparing over here. So you can see the function call over here, a general underscore name compare over here, and as you can see that this is where the vulnerability is, and then it simply frees up the memory. So when we run test case, this code is getting executed, right? And now what we are going to do is that we will make a build of this vulnerable version where the vulnerability is present, the file is not patched. We went to older version, and then we will run and we will see what happens. So again, we need to repeat the same command, that is configure. I will use vulnerable over here, vulnerable build. So basically it will create the build for our vulnerable version, then we'll do make and we will do make install. So in my case, I have already done that. So we will save some time. And now let's go ahead and run that v3 name paste. So I think by default, if we run, yeah, it will take the system file over here, as you can see. So we again need to use ld uh, library path, and here we will use vulnerable build and this too. So we have to use, yeah, so I need to use the correct directory. I have saved it inside build underscore clang path. So you can see we are getting one heap buffer overflow error over here, but for some reason our symbol are not coming. There is some error over here, so we need to use some fix. And that is, we need to use the correct asyn symbolizer. So I will simply export it, and now when we run it again, you can see that we are getting the detailed error message, as well as we are getting the call stack and every detail. So if we see the call stack over here, you can see that the function which is called over here is taste general name compare, that we have seen in the taste. Then it calls general name compare, then it calls asyn type compare, and then it calls asyn string compare. So first it calls async type compare, and then it calls async string compare. That is the root cause of the problem over here. And why is that? Let us go ahead and see the source code. So first we will see this code that is inside v3gen.c. So this is the code, and as you can see, when this general name compare function gets called, it expects two parameter. Again, there is a check which will check a pointer type, and if it is like of type uh, gen underscore x400, then it will call this function. But when it call this function, if we go to this function, right, uh, you can see that what it does is that it will again check a pointer type, and based on that it will call a function. So in our case, what it will do is that it will call this function, that is asn1 string compare, and over here you can see that it is typecasting, it is using typecasting. So our pointer is of asn1 type over here, from where from that it is changing its value to asn string, and then it is also using a pointer value dot pointer value over here. So this is what causing all the confusion over here. And then if you go to asn string compare function over here, you will see that it basically compares two string, right? So the type is string over here, and it like subtract the length a dot length b and b dot length, and then it calls mem compare over here. So then it accesses the data a data b data and a dot length. So since the pointer has been changed over here, like you see this is a string pointer, but if you go to the previous call over here, right, so it has been changed. So that is why this is causing all the issue over here, because the pointer will get the wrong values. So that was the root cause of this problem. And if you go ahead and if you see the call stack over here, it gives you the detailed uh, data, like what is the issue and what has actually happened. So if you want, you can actually use gdb debugger to debug this issue, but I am not going into that detail right now. If you want, you can take it as an exercise. You can debug this issue at your own. And now what we can do is that we can write a simple uh, LibFuzzer harness to fuzz this program. So if you remember the code, what actually happens. So let me open that file. Okay, so we see this particular test case, what actually happens over here. Based on that, we can simply write a LibFuzzer harness and we can fuzz that. So let me go to that function. Okay, it is over here. So if we get some hints, so basically we need to use general name. We need to create two variables, name A, name B, and then we need to use this function, that is d2i underscore general underscore name. We'll generate one name which will be saved in name A, and then we will again use same function and we will save it in name B, and then we will simply call general underscore name underscore compare with this to name A and name B parameter. And then if we provide like mutated data, if we provide first data to this, then there are chances that we will find this particular CV, that is CVE-2023-0286. So with that, let's go ahead and uh, write a very simple LibFuzzer harness, and then we will compile and then we will run it. So in my case, I have created this program, that is LibFuzzer harness, and as you can see, it is simply using LLVM fuzzer takes one input, which takes two standard parameter, that is data and size, and then we are calling this name A, name B. We are calling malloc over here. We are simply doing some sanity checks. Then we are assigning the data, which is mutated data, to that variable, and then we are calling d2i general name first time, second time, and then we are calling our vulnerable function over here, and we are like freeing the memory. So this is a very small program, but this is a LibFuzzer harness, and what we can do now is we can simply compile our this program using this command, that is clang or clang absentee is equal to fuzzer, because we are using LibFuzzer. Then address undefined, ggdb, that is debug build, optimization is 0, v3 name first dot c, output v3 name underscore first, and we are linking with our vulnerable library, and I'll crypto, and let's see what happens. So we have created one build, and now let's run our fuzzer and see what happens. So we will run v3 name underscore first. Okay, and let's see what happens, how much time it takes to find this vulnerability. So okay, it is finding leak sanitizer, so we don't want that. So we can disable that using assign option, detect leaks is equal to 0, then again the same command, and now let's run it, and now let's see what happens. So we immediately found the heap buffer overflow, and you see the call stack, it is same general name compare, assign type compare, and assign string compare. So this means that LibFuzzer can easily find this particular CVE uh, within a second, within few seconds, as you have seen in this video. So uh, this is the beauty of fuzzing, that if you use it properly, if you have proper harness, then you can find any issues within seconds. So as you can recall, we did not give even a single corpus as well, so it is generated one file. So let's go ahead and see the crash file over here. So the crash is 03. Okay, let's do one thing. We can see this crash 0346220. Okay, and you can see that this crash file, it contains A300. So this is the same test case if you see it over here, right? A300. So you can see that LibFuzzer has found the exact same bytes which has been given in this test cases, and which we have actually not used. So this is how you can replicate any of the OpenSSL issue. I hope that you have liked my video. Please do like, subscribe, and share my YouTube channel. That will motivate me to create more such videos. Till the next video, stay safe. Enjoy. Goodbye. Thank you. Bye.